Welcome to sciencecover.com. We're going to look at conduction, what is conductivity, which are the best conductors, why do materials conduct, and why insulation is important. Let's start by looking at conduction. Some materials allow heat to pass through it. We call these materials conductors. Some materials do not allow heat to pass through them. We know these as insulators. But even within these groups, some materials are better at conducting than others. And so we have a value of thermal conductivity. This is a measure of how good a material is at letting the heat pass through it. Silver is a very good thermal conductor. It allows heat to pass through it easily, and so we can assign this a high value for thermal conductivity, such as 420 watts per meter degrees Celsius. Copper is also a good conductor, but not as good as silver, so it has a value slightly less at 386 watts per meter degrees Celsius. Materials that are good insulators have got very low values of thermal conductivity, so plastic has 0.3 watts per meter degrees Celsius. Pause the video and complete task 1. Let's have a look at the answers to task 1. Conductivity is a measure of the rate of heat transfer through a material. So the missing words were conductivity, heat, and material. Let's have a look at the answer to task 1b. We can see that silver is the best conductor on this list, so we can assign silver the highest number, which is 420. We know that copper is also a very good conductor, so we can assign it our second highest number of 386. We know that aluminium is a good conductor, although not as good as copper and silver, so we can assign this a value of 237. We're now left with iron as the only thing considered a conductor on this list, which we can match up to the value of 79. Now we're left with plastic and wood, which we could both consider insulating materials, and both have very low conductivity values. Plastic has a slightly higher conductivity value than wood, so therefore we will assign plastic 0.3 and wood 0.12. We now need to think about why a material conducts. In the diagram, you see a metal bar and heat being applied to one end of this bar. Now, when this happens, the heat energy is absorbed by the metal ions and they will start to vibrate. So that means they move back and forth ever so slightly. These will then bump into their neighboring atoms that will also start to vibrate back and forth, and then these bump into neighboring atoms which start to vibrate back and forth, and in this way the energy actually works its way down the bar. So if we wanted to explain this effect and explain how the heat is actually making its way down the bar, we could say that when the metal is heated, the particles gain energy. This causes them to vibrate. The vibrating particles bump into their neighboring particles and pass on the energy. In this way, the heat moves down the bar. This does not explain why metals are good conductors, but plastics and wood are not good conductors. To explain this, we have to introduce electrons. Inside metals, the electrons are removed from the atoms, which means that the atoms themselves become positively charged. So we have positive metal ions. And then the electrons, which have now been kicked out, are actually free to move around. We call these delocalized electrons. And these can move up and down the wire in any direction that they want. So if we apply heat to this metal bar now, the electrons will pick up this heat and they can travel anywhere they want within this metal. So they will carry the heat with them to different locations. And this is why metals which have these free electrons can actually conduct heat very, very well. Whereas the plastics and woods, which the electrons are still stuck to the atoms, they do not conduct so well. So if we want to summarize this in a few steps, we could say that electrons are lost by the metal atoms, which leaves the metal atoms as positive ions. The delocalized electrons form a sea of electrons. When heat is applied to one end of the metal bar, the electrons absorb this energy. As the electrons are free to move, they carry the energy down the bar. Now pause the video and complete task 2. Let's have a look at the answer to task 2. The electrons are the smaller dark circles, whereas the positive metal ions are clearly marked with a positive symbol, and they're slightly larger than the electrons in this diagram. Let's have a look at the answer to task 2b. Metals have delocalized electrons. The delocalized electrons are free to move. When a metal is heated, the delocalized electrons can absorb the heat and carry it through the metal. In non-metals, electrons are attached to the atoms and therefore do not carry heat. We should now look at insulation in the home. Conductors allow heat to pass through them. However, if we wish to keep our houses and homes warm, then we need to prevent heat from traveling through these. So we use insulating materials that have low thermal conductivity and do not allow heat to pass through them. Good insulators are materials that have poor conductivity. These materials help us keep heat energy trapped inside our homes. Double glazing windows are an example of insulation. It usually consists of two panes of glass with a layer of air trapped between them. Now, air has poor conductivity, and this means that the heat does not pass from one pane of glass to the other pane of glass particularly easily, and this keeps the heat trapped within the home. Some double glazing will have a vacuum between the panes of glass, and this is an even better insulator as there's no particles to carry the heat from one pane to another. Most homes have an inner and an outer wall. The space between these two walls is known as the cavity. And for the majority of history, that cavity has been filled with just air. Air is a poor conductor and therefore has always acted as a reasonable insulator. However, we have materials that we know are better insulating materials than air. And so if we fill that cavity with these insulating materials, then we have created cavity wall insulation. Heat travels more slowly through cavity wall insulation than it does through air, and therefore it slows down the rate of heat loss. Much heat rises in the home and is lost through the attic. So we can place what we call loft insulation in the attic of the home, and this stops the heat from passing through into the attic. Now this material is similar to cavity wall insulation. It tends to be fiberglass material, and we place it on the floor. It has a low conductivity, so again it slows the rate of heat loss. The home also loses heat to the ground, and so if we place any sort of insulating material on the ground, then we can create a layer that's going to trap the heat and slow down the rate of heat loss. So this includes carpets and any form of foam underlay that we place underneath those carpets. Pause the video and complete task 3. Let's have a look at the answers to task 3. Why does a double glazed window insulate better than a single pane window? Well, glass has a low conductivity, so that glass in both cases will act as an insulator. However, if we have a layer of air between two panes of glass, then that is an additional insulator, so it's slowing down the rate of heat transfer. Some double glazed windows use a vacuum rather than air. Why would this be better? Well, a vacuum has no particles, so therefore it's going to lower the rate of heat transfer and be better as an insulator than the air. Question 3. Why is having cavity wall insulation better than a layer of air between the inner and outer walls of the house? So cavity wall insulation has a lower conductivity than the air. Therefore, again, we have a lower rate of energy transfer. Question 4 asks how we can prevent heat loss through the roof of a home. So this is where loft insulation can be added. We know that it's going to slow the rate of transfer or loss of heat through the roof. And how can we prevent heat loss through the ground? We could use a carpet or underlay under the carpets, which have low thermal conductivities, and this is going to act as an insulator, again lowering the rate of energy transfer. Pause the video and complete task 4. Now let's check our answers to task 4.